Hello, welcome back. So today I will talk about surface energy between three phases. So basically, this is vapor phase, this is liquid, obviously, and this is solid. We'll just take this as water, okay? Then we call this either contact angle or wetting angle. Wetting angle. In this scenario, we can treat surface energy as a kind of force. By force, I mean vector. So obviously, energy divided by area should be a scalar term, but we are going to treat it as vector to calculate it. Okay, so basically, this vector is gamma VL. So the surface energy caused by vapor and liquid interface. And this, okay, let me use a different pen. This red vector is gamma SV because it's between solid and vapor phase. And this blue vector is gamma SL. So it's between solid and liquid. Of course, so based on this picture, we can come up with a force, in this case, surface energy equilibrium, which is like this. Gamma SV equals to gamma VL plus gamma SL cosine theta. Then we can analyze this based on the angle of theta because it's a cosine function. It should look like this, right? And we are only gonna analyze theta from 0 to 90 degree, which is pi over 2, right? Because wait. Oh wait, no. Till pi. Because so basically I'll just take it slowly and walk you through it, okay? So between when theta equals to 0, we call this complete wetting because obviously you'll have to draw a picture like this and imagine this angle decrease and decrease until it reaches 0. Then of course the liquid is completely the this surface is completely wet by this liquid, meaning when this is water, this surface should be hydrophilic, right? We already learned this from chemistry that like dissolve in like dissolves like. So because water is hydrophilic, which is polar, so of course this surface should also be hydrophilic. Then because theta equals to 0, cosine theta is 1, then gamma SV equals to gamma SL plus gamma VL, right? In this scenario. Okay, we call this case 1. Case 1, complete wetting. Case 2, partial wetting. Then of course theta is between 0 to pi over 2. It should look like this. right? Theta. Then gamma SV equals to gamma SL plus gamma VL cosine theta. This will be smaller than complete wetting scenario. And at case 3, you know what, let's just not treat this as a separate case. So basically, if this reaches to, it can also reach, it may sound kind of funny, but you can also draw this kind of picture like this kind of case where this wetting angle equals to 90 degree exactly. So this is also possible, all right? So it is included in this scenario. Actually it is, yeah, it is just every angle is included. So basically you can also draw this kind of picture like this. Then this is the wetting angle, which is bigger than pi over 2, right? This can also happen when this surface really don't like this hydrophilic water. If it's really like repelling each other, then this kind of scenario is also possible. And case 3, which is not wetting at all. It looks like this. You can see that theta equals to, it's look like this, right? Like this. This is theta. Theta equals to pi. Then cosine theta should equals to -1. Then gamma SV equals to gamma SL minus gamma VL. So when you draw diagram, which is gamma SV versus theta, it should look like this. So when theta increase, gamma SV will decrease. What does this mean? Meaning doesn't mean, okay, doesn't mean theta get bigger, gamma SV will get smaller. Why don't you think about it? So there is water here. If this angle is bigger, doesn't mean gamma SV gets smaller. Well, of course no, because this surface doesn't change. Regardless of this liquid, it doesn't matter what kind of liquid you put there. What matters is the surface itself. Gamma SV is an intrinsic property of that material, and it has nothing to do with what kind of liquid you put on it. So, of course, this diagram is just an experimental diagram you got. So basically, you put the water there, you measure this angle, then we can measure how big this material's gamma SV is. It doesn't mean this material's surface energy will change with the angle. I hope you understand what I mean. So, sorry. Wait a second. So, Uh, Basically, if you when you Google um, surface energy of certain material, what you will get the data of gamma SV. This V here it means water. It means air. It means air surrounding us. So gamma SV is an intrinsic property. It doesn't change with the shape. Gamma SV doesn't change with the type of liquid you put on it. Nor the shape of the material. Okay? Gamma SV only depends on gamma SV only depends on the material itself, on the material's microstructure. Then you can realize that what causes this theta to increase. Of course, the more hydrophobic the surface, the bigger theta, right? The bigger theta indicating lower surface energy between this material and this air and the air surrounding us. Well, of course, they're going to tabulate the data based on air because we are material scientists and we want to know this material's surface energy in the air we breathe, right? Of course, it's just like we treat everything in standard state, which is 298 Kelvin, room temperature, right? It's the same manner. Anyway, all right. So that's all for today. Thanks for watching.